All right, y'all. It's a little bit after 2. We're going to go ahead and get started. This first question, you have to predict whether a precipitate will form as a result of the following reactions. And if a precipitate does form, write the products and identify which product is the precipitate. So we're looking at 2 double replacement reactions, and we're trying to figure out, are we forming a precipitate or not? In the first one, do we form a precipitate? Do we form anything that would be insoluble in water? And if you're stuck or you need help, you can say stuck or help or I don't get it. All right. So in A, if we were to swap those ions, we would pair up the magnesium. That should be a 1 there. We'd pair the magnesium with the chloride and the sodium with the sulfate. Then we use the solubility rules to figure out if either one of those things is insoluble. Halides, which is what the MgCl2 would fall under, they're generally soluble. Sulfates, also generally soluble. So that means there's no precipitate here. So there's no reaction. Both of those are aqueous, so nothing would form. For B, if we were to swap ions, the silver would then be paired with the iodide ion, and the strontium would be paired with acetate. Acetates, soluble. Halides are usually soluble, except silver, mercury 1, and lead 2. So for B, you would form a precipitate, and it would be silver iodide. Those questions seem to be a little bit tricky sometimes, so I wanted to start by going over those. Yes, you will get the chart. And speaking of the exam, I've decided to make the exam take home. There's a lot. There's the charts and all the equations and stuff, like for knowing how to solve the Chapter 8 problems. And what I really want to know is that you can use that information and apply it to a new problem versus can you memorize how to do a problem. So it will be a take-home exam. I will post it. You can use your notes. You just have to do it by yourself. So it's an individual effort. Okay. Yes. No. So for the first 5 rules, everything here is soluble except for what's in parentheses. So silver, mercury 1, lead 2. So everything that has an alkali metal or ammonium, acetate, nitrate, halides, or sulfates, all of those things are soluble in water, unless otherwise noted. Rule 6 through 10 is saying all of these things are insoluble, but here are some exceptions. Does that make sense? Yes. But now you got it. So there you go. Yes. It's magnesium. Because if it's not, so halide ions are generally soluble, except for when you have silver, mercury 1, lead 2. It's not one of the exceptions, so that means it must be soluble. These are like those logic puzzle things that you had to do in elementary school to try to figure stuff out, so it just takes a little practice. Go for it. So, if it's soluble in water, that means it's going to be aqueous. If it's insoluble, that means it's a solid. Those are the only two things we're going to be dealing with when it comes to a double replacement reaction. It's either aqueous or solid. Other questions, or are we ready for the next exam review question? Okay. So I'll give you 2 minutes. This is using the activity series and determining which metals will react with sulfuric acid and which ones will not. We'll go over it. So the key here is figuring out where hydrogen is, which is what the metal would replace, versus all the other metals. All the metals that come before hydrogen are more reactive and therefore will replace it in a reaction. All the metals that come after hydrogen in the series are less reactive and will not replace it. So let's find all the metals. There's silver, tin, cobalt, and manganese. Anything that comes after hydrogen, there's going to be no reaction. For all the other three, they will react. Yes. Mm-hmm. Let's move on to the next one. Now you're going to do some math. I'll give you a couple of minutes to set it up and try to get to an answer. Then I'll start setting it up. And this is a density question. I'll start setting up the problem. If you're not finished, that's okay. And if you're stuck, I might be able to help you get unstuck. We've got an unknown gas, but we know its mass and what volume it occupies at STP. We have to figure out what the molar mass is. Seems like those are two unrelated things, but that's not true. For gases at STP, we have two definitions of density. We have mass divided by volume, which we talked about in Chapter 2 when we were going over the density of solids and liquids. But at STP, for a gas, the molar mass divided by molar volume will also give us the density. We know the mass and the volume, and molar volume, which I abbreviate MV, is 22.4 liters. That's just something you need to know. And that comes from the definition. If you have 1 mole of gas at STP, doesn't matter what the gas is, the volume will be 22.4 liters. You substitute in everything that you know. So we've got our mass of 25.4 grams, our volume. We don't know the molar mass, but we do know the volume. So you cross multiply, divide by 15.9, and you should get somewhere in the ballpark of 35.8, 35.6, something like that. Does everybody understand that one? So that's not on the exam review that I posted. So there's a benefit to participating in class because sometimes you get extras. You will see a problem like this on your exam. I already made it, so I can tell you. You'll see one exactly like this. Just different numbers. We good here? Great. This next one is a Chapter 8 question. And it's incorporating everything we did with the percent composition, empirical formulas, and molecular formulas. So I'll give you 4 minutes for this one, and then I'll check in and start solving it. I'm going to start setting up the problem. You can keep working or put your answer in the chat as you work it out. So whenever you see one of these problems where you have a percent composition, you need to assume 100 grams before you can do anything with figuring out an empirical formula and a molecular formula. So instead of 85% and 15%, we can say 85 grams of mercury and 15 grams of chlorine. We convert those to moles. So when you do this, you see that they're pretty close, right? So that's going to be 1 to 1. But if you wanted to do the division anyway, just to check, remember that you can write it as a ratio. And that's going to give you about 1, which means 1 mole of mercury for every 1 mole of chlorine. For our empirical formula, that means we have HgCl. We're only halfway done though. Now that we have the empirical formula, we have to figure out, so how do we put that in the calculator? Which part? The ratio part? So you would divide 0.424 by 0.423, and you would get 1. But you have to know that that 1 means 1 mole of mercury for every 1 mole of chlorine. Okay. Once you have that empirical formula, you need to figure out its molar mass. And I'm not going to write it all out here, but you should get somewhere in the ballpark of 236 grams per mole, give or take. Then you figure out your N, which is the molar mass of the molecular formula divided by the molar mass of your empirical formula. You should get about 2. It's like 1.99 or something like that. That's 2. That means you're multiplying your empirical formula by 2. And that is your molecular formula, Hg2Cl2. Yes, good job. Do we have questions on that? Again, you will see a problem like this on the exam. Alrighty. Next problem. You've got some ethane gas, and you're trying to figure out the volume. I'll give you 2 minutes. I'm just going to start writing out the solution. We have a mass of 7.5 grams, and we're trying to figure out a volume. The only way that we can get there is through moles. So we've got 2 simple problem types. The first is mass to moles. And the second is moles to volume. We're going to keep going and then I'll let you know. For mass to moles, you're going to use the molar mass of ethane. So you should get somewhere in the ballpark of 30 grams per mole for that. And if you need help with calculating molar mass, let me know. So yeah, 30.07, 30.068, you're going to get the same answer. To go from moles to volume, you need molar volume. That's our unit equation. 1 mole is equal to 22.4 liters. And from there, we can write a unit factor that suits our needs. Starting with the mass in grams, we're going to first convert to moles. Then we write a unit factor from our unit equation for molar volume. We want liters at the end, which is a volume. So those will go on top, and the moles will go on the bottom. When you do that math, and with sig figs, 5.59 liters. So remember, there's 3 sig figs in our given information, so we should have 3 sig figs at the end. Questions on that one? So if you put 5.60, you would get full credit for that. All right. That's all that I had for exam review. We did some problems last week. So between last week and this week, and the rest of the problems on the exam review on Blackboard, that should put you in really good shape for the exam. For those of you who have just joined us, exam 4 is going to be a take-home exam. So you may use your notes. You just have to make sure you do it on your own. You'll post your answers as a PDF along with all of your work, just like you do the chapter check-in. So you'll show your work, make sure that your answer is clear, box it or something like that, and you'll upload it to Blackboard as a PDF, and I will grade it. You'll get partial credit if you set up the problem, but you don't get the right answer. So the more work you show, the more likely you are to get partial credit, even if you don't get the right answer. If you get the right answer, but you don't show any work, you will not get full credit. I need to see your work. Show me how you set up the equation. All of that will be posted on Wednesday in a folder called Exam 4. The only difference is you have to have everything uploaded by Friday, 11:59 p.m. If you try to upload it after that, you will not see the assignment to do so. So make sure that you do it and upload it before the end of Friday. Is that clear? We'll talk about it again at the end if we have time. Yes. We may not have time, but if you can stick around for 5 minutes, then I can dig and find one for you. Other questions? Or just let me know if you're ready to move on. I will take your silence as ready. All right, there we go. So we're starting chapter 9 this week. We're spending 2 weeks on it. There's more math involved. So if chapter 8 was a struggle for you, and it's still a struggle, you need to figure it out. Come to office hours tomorrow, send me a course message through Blackboard, send a carrier pigeon, something. Let me know, get a tutor, work with a friend who's in the class that gets it, something. Because you need information from chapter 8 to go forward to chapter 9. So we've been talking a lot about chemical equations. We started that kind of in chapter 7, where we were writing chemical equations in words, taking the words, writing chemical equations, balancing. Then we started talking about moles in chapter 8, and doing moles to mass, mass to molecules, and all those kinds of things. Now we're going to wrap all those together. We're going to start by looking at chemical equations again. When you look at a chemical equation, the numbers in front of each compound are the coefficients. If you don't see one, you assume that it's a 1. If we were to talk about this in terms of how we're forming nitrogen monoxide, we could say 1 molecule of nitrogen gas comes together with 1 molecule of oxygen gas and creates 2 molecules of nitrogen monoxide. Somebody's microphone is still on. Just gonna throw that out there. We can say that about molecules. We can also say that about moles. If I had 1 mole of nitrogen gas and 1 mole of oxygen gas, I would make 2 moles of nitrogen monoxide. So these coefficients that we see when we're balancing equations, those can be used to talk about the number of moles of reactants and products. But this is only for a balanced equation. Everybody with me so far? We can use those balanced equations and the coefficients to write mole ratios. Mole ratios just describe the relationship between the reactants and the products. Sure, I can go back. So if I wanted to write a mole ratio for nitrogen gas and oxygen gas, I would look at the chemical equation and I would look at the coefficients for each and write it as a fraction. You can also write the reciprocal. Let's say I wanted to write a mole ratio that describes the relationship between nitrogen gas and nitrogen monoxide. You can put it in the chat. What's one mole ratio that I could write for these two compounds? Remember, we're just looking at the coefficients. So we're just trying to get one mole ratio that describes the relationship between nitrogen gas and nitrogen monoxide. So you're looking at the coefficients. Here's nitrogen gas, nitrogen monoxide. And you're literally taking that and writing it as a fraction. We can write 1 mole of nitrogen gas for every 2 moles of nitrogen monoxide. Don't forget about that 2. Whatever number is in front of the compound, that's how many moles you're writing. Once you have one relationship, you can write the reciprocal. How about you give me one for the oxygen gas and the nitrogen monoxide? What is 1 mole ratio that we can write? And you can just put the numbers too, because typing out all the moles and everything might be, it's a bit much. So that's writing mole ratios. We're just looking at the chemical equation and writing down the coefficients as moles, and we're writing that like a fraction. I want you guys to do some practice. I won't ask you to put it in the chat because it takes a while, but I want you to take a minute and write 2 mole ratios that describe the relationship between mercury 2 oxide and mercury. Don't forget that this is available on Blackboard. So if you miss something, you can also go back and just look at the notes. We may not be able to keep going back and pausing. So just keep that in mind. Okay, yeah, that works too. You can take a picture. So write in your notebook 2 mole ratios that describe the relationship between mercury 2 oxide and mercury from this chemical equation. I'll give you a minute, and then I'll write them out. Okay. We're looking at mercury 2 oxide and mercury. Sometimes it helps to circle the ones that you're interested in so that you're not tempted to write anything about oxygen or the other compounds And this will come into play more so when we start doing stoichiometry problems. Right now we're building foundation. So using our chemical equation, these are the two mole ratios that we can write for mercury 2 oxide and mercury. How does everybody feel about writing mole ratios? Do we need some more practice, or do you want to move on to the next concept? Because I have some more examples you can try, or we can move on to the next concept. All right, we got a vote to move on. All right, a couple of votes to move on. So if you need more practice, here's another one. I will put the answers into the PDF before I upload it. So if you do need a little more practice, you can do this on your own time. The reason why we care about mole ratios is because we can build to do problems that will solve for, if I have this much of this reactant, how much product will I make? Or I made this much product, how much reactant did I start with? We started with just the mole ratios. Now we're going to do mole to mole calculations. And all that means is we're taking moles of one substance in the chemical equation and using a mole ratio to determine how much of another substance in the same chemical equation. Our first example problem, we've got how many moles of oxygen gas are produced when 3.5 moles of mercury 2 oxide are decomposed. I like to write out the question, just like with most of these math problems. My starting information is 3.50 moles of mercury 2 oxide. I'm trying to figure out how many moles of oxygen gas. So that helps me so I know what my mole ratio should be. Take a second and figure out what mole ratio I need to put here if I'm trying to take the moles of mercury 2 oxide and figure out how many moles of oxygen gas I will make. And you can just put the numbers in the chat, like, 1 to 2 or 2 to 1 or whatever it is. You don't have to write out all the moles. So just like we were doing with our mole calculations in chapter 8, we want to write the mole ratio that's going to cancel out the units we have and leave us with the units we want. One thing that may be helpful to you is when you're setting up these problems, if you write out your plan like I do, where you have your given information and your question, the form of your mole ratio is always going to be whatever your question is over your given. So the question has to do with moles of oxygen gas. So you're going to take the moles of oxygen gas from the equation. The given was moles of mercury 2 oxide. So you're going to take your moles from your equation. So if it doesn't quite make sense to you how to get that mole ratio, if you set up your problem the way that I do exactly, then you can use this. Just remember that your mole ratio uses the chemical equation, not the given information in the problem. So I want you to try one on your own, and then I'll check in with you. Same equation, but this time we're trying to figure out how many moles of mercury 2 oxide decomposed to produce 5 moles of mercury. I'll give you 2 minutes, and then we'll go over it. I'm going to start setting up the problem here. We're given information about the moles of mercury. We're asked about the number of moles of mercury 2 oxide. We need to write that mole ratio. We're trying to get rid of the moles of mercury, so we'll write those on the bottom. That leaves the moles of mercury 2 oxide for the top. You don't really have to touch your calculator for this one. But if you did, that's okay. You should get 5 moles. How do we feel about these? Because this is really the crux of all the other calculations we're going to do. Writing the mole ratios and knowing how to use them. Great. Do you guys want to try this one, or do you want to move on? Then go ahead and try this question. We got a couple of votes for try it. Okay, so let's go back for a second because we have a question. So with this one where we had the mercury and the mercury 2 oxide, we had to write a mole ratio where we could cancel out the mercury and be left with the mercury 2 oxide. We have to relate these two, and we're trying to figure out how many moles of mercury 2 oxide were decomposed to make 5 moles of mercury. So our choices for mole ratios were these. And we had to choose the one that's going to give us moles of mercury 2 oxide at the end. Does that help answer your question a little bit better? Alright, so with that in mind, try this problem. I'll give you another 2 minutes. I know some of you are ready to move on, but I want to make sure everybody gets the practice that they need. Here we go. This time we're talking about forming hydrogen chloride gas. We've got some chlorine gas, and we're trying to figure out how much of the hydrogen chloride gas will make. For our mole ratio, we need to have something that relates chlorine gas and the hydrogen chloride gas. So our options are here. And if you feel like you need to write out the 2 mole ratios and then choose the right one, that's perfectly fine. And that is a great way to make sure that you don't mess it up. We're going to use this first one because we'll be able to have moles of HCl as our final unit. There's a question, will it always be 1 or 2 for the mole ratio? So the mole ratio just depends on what the coefficients are, if you mean in terms of what these numbers are here. If you're talking about which one as in A or B, it depends on the problem. Does that answer your question? Yeah, I can repeat it. So in terms of the actual coefficients in the mole ratios, that's completely dependent on the chemical equation. So far, we've just been working with really simple ones that have coefficients of 1 or 2 for each of the compounds. In terms of which mole ratio, A or B, that's going to depend on what you're trying to figure out. So it's never always going to be A or always going to be B. You have to figure that out on a question-by-question basis. When you do it all out, you should get 1.5 moles of hydrogen chloride gas. Other questions on this? Now we're going to get into the heart of Chapter 9, which is doing stoichiometry problems. We've built up the foundation of Chapter 8 with understanding the mole and how to convert from moles to mass. We've talked about mole ratios and how we can interpret chemical equations. Now we're going to start doing some stoichiometry problems. The first type that we're going to cover is mass to mass, where you're given the mass of one reactant or product, and you need to calculate the mass of another reactant or product in the same chemical equation. I think it's best to do that by showing an example. So this is the same example that I did in the YouTube video, which you may not have had time to look at. But I'm going to go through it and you can ask questions versus just watching it. Sure, I can go back. There isn't anything on there except for one thing. No problem. So I did this example in the YouTube video, but you'll have the opportunity to ask questions, which you obviously can't do when you're just watching the video online. Then we'll go through one together where I'm asking you questions. Then I'll let you do one on your own. So that's the process we're going to do for these types of problems. What is the mass of mercury produced from the decomposition of 1.25 grams of orange mercury 2 oxide? You'll notice we've been working with this same equation. That was on purpose because I knew we were building up to this example. When you're doing these problems, you won't have the privilege of a title that says mass to mass problem. On an exam, you'll have to figure it out yourself. The way you do that is by identifying what the given information is and what the question is asking. Our given information is 1.25 grams of mercury 2 oxide. That's a mass. And we're trying to figure out the mass of mercury produced. Always take the time to identify the problem type. This is a mass-to-mass problem. Now that you know what type of problem it is, when you have your Rolodex of problem types, you can just pick through and choose the one that makes sense to use to solve the problem. I'll give you the generic formula for how to solve this, and then I'll put in our actual numbers. So if you have a certain number of grams of substance A, the first thing you need to do is get to moles. With all of these calculations that we're doing, you should notice a theme. Grams, can't do nothing with it. You have to convert to moles. The way we convert from grams to moles is using the molar mass. If you're a color pencil type person or a colorful person, great time to pull out the markers or the color pencils, highlighters, whatever. Once we've converted to the number of moles of A, we can convert that to moles of B. So whichever substance we're supposed to be figuring something out for, that's what we do. That's going to rely on what we were just doing. And you need a mole ratio of B to A. And again, I'm going to make this a little more clear with our actual example. The final step for mass to mass is to take those moles of B and convert them to grams of B using molar mass. But this time, you're using the molar mass of B. To put it into context, the mercury 2 oxide is our A, and the mercury is our B. So if I were going to write it out again for this specific problem, we'd be starting with grams of mercury 2 oxide and converting that to moles. Then we convert those moles to moles of mercury using a mole ratio. In our generic one, we said B to A. Now we can write what that actually is. Our B is the mercury, and A is the mercury 2 oxide. Then we convert that to grams of mercury using the molar mass of mercury. That's the plan every time for a mass-to-mass problem. Are you still with me? We haven't done any numbers yet, just talking about the plan. So make sure that you have that top part in your notebook, okay? The molar mass for the mercury 2 oxide has already been provided. That will not always be the case. The molar mass for mercury, you can just look at the periodic table. Now that we've got our molar masses, we can actually fill in the numbers for this. So we're going to start writing our equation. That's our given information. The first unit factor has to do with the molar mass of mercury 2 oxide. We're trying to go from grams to moles. So those grams are going to go in the bottom. And the 1 mole goes in the top. Next is our mole ratio. In our plan, we said it's B to A, which means the moles of mercury over the moles of mercury 2 oxide. Moles of mercury, we've got 2 moles. Mercury 2 oxide, 2 moles. The final piece is converting our moles to grams. So right now, if we were to stop, we'd have the number of moles of mercury. If we multiply that by the number of grams in 1 mole, then we would get the mass. Yes, sir. No. No, you would not. That's the molar mass. The molar mass has to do with how much 1 mole of your substance weighs. Always and forever. Okay? Yes. The subscript would tell you. All right. Good, good. So, I always like to check and make sure that my units cancel. And this is why I write out the plan every time, because my plan tells me what units I should end up with. And I just like colors, I'm not going to lie. So we're starting with grams. Those cancel. And I have moles of mercury 2 oxide, just like in my plan. The next step, I'm canceling out those moles, and using the mole ratio to get to moles of mercury. The third step, I'm using the molar mass of mercury to get to grams, which is where I want to be at the very end. Remember, when you're doing an equation like this, if you have a number in the bottom, the denominator, that isn't 1, meaning it's bigger or smaller than 1, you have to divide. So don't forget that. Don't just multiply everything. You're multiplying and dividing here. Try putting this into your calculator and let me know what you get. Yeah, Whitney, that's what I got too. With sig figs, you should get 1.16. So this is the calculator test to make sure that you can get it all in there, because it's a lot. And each calculator is different. So you should do, so you can break it all up if you have, so I use a TI-89, an 83, you can do it the same way. If you have something other than that, other than a scientific calculator, you may need to break it up. But you're going to do 1.25 divided by the 216.59. Then you're going to, you can put that in parentheses if you want. Then you could multiply by 2 over 2, which is 1. Okay. Yeah, no, you can't do that. You have to do everything in order. So you take the 1.25 and divide by the first number. Then you move on to the next one and you handle everything there. Multiply and divide. So order of operations, they matter. Can I move on to the next slide where we try one together? Oops. Whoa. Okay. Same type of problem, but this time we're looking at the mass of oxygen. What is the mass of oxygen produced from the decomposition of 3.85 grams of mercury 2 oxide? Always make sure to do that first so you know what type of problem you have. For a mass-to-mass problem, we're always going to need molar masses. I just used 32 for the molar mass of oxygen. Now we need to write out our plan. Starting with the grams of mercury 2 oxide. What do we have to do to it first? Figure out the number of moles. Once we have the moles of mercury 2 oxide, what's the next thing we have to figure out? We've got to use the mole ratio and we're trying to get to the moles of oxygen. The last leg is answering the question. So we need to get to the grams of oxygen using the molar mass of oxygen. Using this plan, I'll give you 2 minutes to set up your equation and try to get to an answer. I'm going to start writing it out, but feel free to keep working. Good job. So it may take you a few more minutes to be able to get through it, and that's totally fine. These problems take a while to master, and it's just a lot to write out. Let's just be honest about it. But I've been doing this for years. I almost said decades, and that scared me a little bit. That might actually be true. Approaching multiple decades. So don't feel like, oh, I'm taking too long, or I should get it by now. I've been doing this for a long time. And some people may have had chemistry and it's all coming back to them. So it could be something that comes a little more naturally. If you're someone who needs a little more time to digest, that's okay. If, however, you find that you need help, you can always come to office hours or send me a message. So how do we feel about these so far? Here's what we're going to do. I want you to do this problem on your own, completely on your own. I'll give you 5 minutes to start. Then I'll start setting up the problem, and we'll go through the answer. Then we'll take a quick break. So 5 minutes, set it up from start to finish, and then I'll jump in and start writing some things down. If you get stuck, that's okay. Let me know where you get stuck so I can point things out and kind of help you out. It looks like folks are starting to finish, so I'm going to start writing because it's going to take me a minute. I'll start by writing out the plan. So that's our plan. Yeah, you should get something like 27 grams. I'll show you how. Here we go. So make sure that you actually started with 25 grams, not 2.5, but 25. Yeah, I saw that lady and I was like, oh, she's so close. Yeah, 25. Yeah, I knew you forgot something in there, Patrick. So that's what you should have for your equation, and you should get 27 grams of mercury 2 oxide. This is a good place to take a break because we're going to switch to another problem type. So take 5 minutes, shake your brain out, and get ready for another problem type. So I'll see you back at, we'll say 3:45. Okie dokie, y'all. We're going to get through one more problem type, and then I think that'll be about it. So we just did mass to mass. That's where we're taking grams of one substance in a chemical equation, converting it to something else in the same chemical equation. For this second type, we're given the grams or the mass of one reactant or product, and we have to figure out the volume of the reactant or product. Since we're talking about volume, that implies that one of these is going to be a gas. Well, then that means that, yep, application sharing is reconnecting. Yeah, every once in a while, Blackboard, their servers get so overwhelmed sometimes that screen sharing disconnects for a minute. So we'll just let it come back. So that 5-minute break may turn into more like a 10-minute break. So if you got a little extended break, that's fine. So we had an extra 5 minutes. The second problem type we're going to have time to go over today is mass to volume. Yeah, you should be able to see it now. So mass to volume problems, that means that we're talking about one of the reactants or products is a gas. Maybe I just need to switch slides. Either way, mass to volume. We'll do just like we did before with the mass to mass, where I'll show you the example that I did in the YouTube video, and then we'll go through an example together, then you can try one on your own. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid at STP? Ways that you know you're dealing with the mass to volume problem. The first is you're given a mass. And you're asked something like how many liters or how many milliliters. Since liters and milliliters are both volume, you know that's a mass to volume question. The other hint that lets you know that you're dealing with the volume is that we're mentioning STP, standard temperature and pressure, which we only talk about when we care about gases. Now that we've identified the problem type, I'll write out the generic how you solve the problem, just like I did before. If we're starting with a mass, grams of A, we're going to do the same as before by converting to moles. We always have to convert to moles because that's far more useful. You'll do that using the molar mass of A. Then we have to get from moles of A to moles of B. Same thing. We'll use a mole ratio of B over A. So far, no changes. The last step, however, instead of going to grams of B, we're going to a volume. So we're going to stick with liters here, but you may be asked about milliliters. To go from moles to liters, we have to use molar volume. That's the only step that's different. To put it into context, the aluminum is our A, hydrogen gas is the B. We'll start by taking the grams of aluminum and converting to moles. Then we convert to moles of hydrogen gas using a mole ratio. The final step, we're going to use that molar volume, which I'll abbreviate MV, to go from moles of hydrogen gas to liters of hydrogen gas. Is everybody with me so far? Okay. Next, we're going to put in our numbers with this. We're starting with 0.165 grams of aluminum. You can use the periodic table to figure out what the molar mass is. Then we fill in our mole ratio. What's the mole ratio going to be if we're trying to go from moles of aluminum to moles of hydrogen gas? Yes, we're going to have 3 moles of hydrogen gas on top and 2 moles of aluminum on the bottom. There's a lot of other compounds here. We don't care about those. And sometimes when you're in a test situation, you may try to incorporate the hydrogen chloride or the aluminum chloride. Don't. You only care about the 2 things in the problem. The final step is to use molar volume. Now I gave you the unit equation. 1 mole is equal to 22.4 liters. What am I writing in the top of this unit factor? Yes, it's the 22.4 because we're trying to get to liters. That's always going to be what the unit factor is. So we got that because we're trying to convert the moles of hydrogen gas to liters. In order for that to happen, we've got to choose between the two unit factors we can make. Whenever you're doing a mass to volume problem, specifically starting with mass, ending with volume, because you can reverse it, and we will eventually, your unit factor for the molar volume section will always be 22.4 liters for every 1 mole of gas. We can cancel out our units and walk along our plan. The first stop was making moles of aluminum, which we did. Then we used a mole ratio to convert moles of aluminum to moles of hydrogen gas. Then we used molar volume to convert to liters. And yes, you should get 0.205 liters of hydrogen gas. Not that much different. Can I move on to the next slide? Okay. So here's what I want to do. Since these problems are so similar to mass, I want you to try to set this one up on your own. I'll give you 5 minutes. Just try to get to the point where you're about ready to write an equation. If you can get to an answer, that's great. Put it in the chat. But I want to give you 5 minutes just to get started. I'll start setting up the problem, and then we can figure out what answer is correct. How many liters of oxygen gas are produced from the decomposition of 14.6 grams of sodium chlorate? We're starting with the mass, and we're asked about liters of oxygen gas. So this is a mass to volume. Like I said, you'll want to get in the habit of identifying the problem type before you start doing the math. You'll need to figure out the molar mass of sodium chlorate. Not going to write it all out, just tell you what I got. But if you're having trouble with figuring out how to calculate the molar mass from chapter 8, let me know. I'll write out the plan first, and then I'll write out the equation. So there's our plan. Now I'll put some numbers to it. That's what your equation should look like. May not be as colorful, but you should have the same numbers. When you do all that math, we need 3 sig figs here. So I got 4.61 liters of oxygen gas. How did we do on that one? I know a couple of y'all got it. I want to check in with everybody else. Okay. So we've got a couple of options here. We can do another mass to volume problem, or we can move on and switch it up and do volume to mass. So vote for mass to volume or volume to mass for the next problem that we do. Okay. So let's move on. I'll put this answer into the notes before I post it. We'll go through an example, and then we may have time to do one together. So volume to mass, it's the reverse of mass to volume. So you're starting with a volume of gas, and in this case, we're starting with oxygen gas. And we're asked about how many grams of sodium chlorate are needed to produce that amount. The plan is going to be pretty similar. We'll do the generic one first. We're starting with liters of A. We have to go from liters to moles. Use molar volume there. The middle piece is always going to be converting from moles of one thing to moles of another. That's where our mole ratio comes in. Then we need to convert moles of B to grams of B. And that's using the molar mass. So it is the opposite. We're just flipping those two steps. Molar volume is at the beginning, and molar mass is at the end. The oxygen gas is our A. The sodium chlorate is our B. You can start solving it on your own if you want to, while I'm writing out the plan and everything else. And you can share your answer in the chat if you'd like. Otherwise, you can just write along with me and do the example with me. So that's our plan for this particular problem. And from last time, we already know what our molar mass is for the sodium chlorate. We're starting with our oxygen gas. And now we need to write a mole of a unit factor for the molar volume. We're trying to go from liters to moles, which means we're going to have moles on the top and liters on the bottom. When you're doing a volume to mass problem, that's what your unit factor is going to look like for molar volume. Again, that's volume to mass. Then you put in your mole ratio. And finally, the molar mass. When you do all that math, you should get 29.2 grams of sodium chlorate. And you can look at how the units cancel as well. So I think that's a good place to end. We'll pick up with this problem type next week. And then we've still got one more problem type to go and some other concepts for Chapter 9. So you have your exam this week. I do hope that you can get some time in to watch the Chapter 9 video so you can be ready for next week. Are there any questions about this? Okay, so we'll skip ahead. So here are your reminders. Exam 4, it's going to be take home. It's going to be available Wednesday. You have to upload your exam before the deadline, which is Friday, October 30th at 11:59 p.m. Make sure that it's a PDF. Make sure that you don't just... We're going to do it next week. So all that we didn't finish, we're finishing it next week. We have 2 weeks to cover Chapter 9, so don't worry. You have to upload your exam by 11:59 p.m. Make sure it's a PDF. Make sure that you don't just submit it and then, you should get that confirmation from Blackboard that you have submitted it. Because if it's not submitted, I can see that you attempted, but it's not submitted, you will receive a 0. I will reach out to you with course messages. I will leave you a note for the feedback for the learner. But if you don't get back to me and give me the proper document, you're going to get a 0 for exam 4. And that would be really unfortunate. So make sure that you double and triple and quadruple check that you have posted the right thing and that it's a PDF. Your Mastering Chemistry is not due until Sunday, November 15th. There's no chapter check-in this Sunday. You have an exam to work on, and I'd rather you work on your exam and watch the video for Chapter 9 to be ready for next week. So those are your assignments. Do the exam and watch the video and take notes. No chapter check-in. And next week, I should have put the 1st. So it's the week of November 1st, but there's no office hours next week. We're still having class, but there's no office hours. So that is the week that I will be gone. Make sure that you get everything you need between now and the end of Tuesday next week. Because Wednesday through Sunday, I am not going to be checking messages. I'm going to be spending time with my family, spending time with my new baby. We'll still have class. But until that class, I will be ghost. And if you're dying, I can't help you anyway. Okay? So no office hours during that week. I'll give you another reminder next week. If you don't have any questions for me, you're free to go. Otherwise, you can hang around, ask your questions.